Good morning, everyone. My name is Shijia Li. I'm the team lead of the Protection and Smart Grid team within the Application Expertise and Electrical Simulation Department at OPAL-RT Technologies. Today, I will present to you a hardware-in-the-loop relay testing demo. It is about traveling wave relay testing with FPGA-based real-time simulator. At the end of this demo, I will answer some of your questions, so please feel free to start sending your questions while watching this demo. So here we can see the hardware setup for this demo. On the right, we have OP4510, which is the real-time simulator that we will use today. The power system model, which consists of the voltage sources, breakers, load transformers, as well as the three-phase frequency-dependent line model, will be executed on the FPGA at a time step which is less than 1 microsecond. And on the left, we have two Schweizer T400L traveling wave-based relay. Between them, there is a fiber optic connection for the TW87 communication channel. And from the simulator, we're outputting the voltage and current measurement at the two buses of the transmission line. And these signals are sent out as plus-minus 4 volt analog out signals at 1 megahertz to the two devices under test. Here, this figure shows the power system model that we are running on the simulator. So we have two voltage sources on both ends of the line, and then we have transformers, some loads, some path section lines. On the two ends of the line, we have breakers. And then for the line itself, we have two segments of frequency-dependent line. The first segment is 8 kilometers, and the other one is 12 kilometers. And we are applying a fault between the two segments. So if we want to vary the fault location, then we will need to change the length of the two segments. The simulation timestamp currently is 670 nanoseconds. And this is automatically determined by EHS solver, depending on all the components you have in this power system model and the complexity of the topology. So to be able to test the traveling wave relay, we have to use a very accurate line model. So here we're using the frequency-dependent line in EHS to run on the FPGA. The frequency-dependent line model, it takes a POM file as input. And this POM file can be created either in EMTPRV using the line model component or in Artemis where we have a wideband and MAR-TFD line feature. So here is the interface of RTLab, and here I created a project called Traveling Wave Example and have already added this model here. And now let's open the model. So on the top level, we have the SC console subsystem for the control that we want to apply in real time. So here we have added some control signal to apply different types of fault. And also here we have the AOMR block, which controls the mapping of the signals. So we can select the first analog out channel. We're mapping it to EHS-Y07, so the seventh signal from EHS. And we could apply a specific gain and offset and also add saturation to the output signal so that it is always within the input range of the device under test. In the other subsystem, which is the SM, the master subsystem, here we have the EHS block, and if we double click on the EHS block, we can specify the power system model. So here, this is the name that we have. And here it opens the power system model that will be executed on the FPGA. So here we have the two FD line segment. And this one, it is using the 8 kilometer POM file, and the other one is 12 kilometers. So the total length of the line is 20 kilometers. Okay, now so let's go back to RTLab and load the model. So once the model is loaded, it will open this console subsystem. And once we start the simulation, we will be able to control the model using these blocks here. Okay, so now the model is loaded. Execute. So now if we open the HMI of the relay under test, we see here are the voltage and current signals. The relay is R, the differential 87, the traveling wave differential element TW87 communication channel is okay. The relay is enabled. So now if we go back to the model, and here we apply a single line to ground fault between phase A and ground. And then remove the fault. We see that the relay tripped. The TD21 time domain impedance-based distance relay has tripped, and also TW87. And phase A and ground are asserted. So now we could get the event record from the relay. So we're going to refresh the event list. And then we're going to retrieve the ComTrade file from the relay for this event for both 10 kHz and 1 MHz report. Since the file transfer will take some time, so I will present to you some of the ComTrade files I saved before. That is with the same model and the same event. Same type of fault at 8 kilometers. So we will open both of the 1 MHz record from the relay on the left and also from the relay on the right. Okay. So here on the top, we have the current and voltage signals from the relay on the left. This is the 1 MHz recording. If we zoom in the waveforms, we can really see these step changes, which will be taken as the traveling wave signal after the differentiator. And bottom left, we have the operation signal of the different protection element, the differential traveling wave TW87 time domain distance, traveling wave 32, and the last one is also edge to ground for time domain distance protection. So if we zoom in to where the fault occurs, where the orange cursor is, and then for the pink one, we move it to where TW87 trips. So it took 953 microseconds for the T400L relay to pick up on this fault. So this is very fast. For the TD21 is around 6 milliseconds, which is also very fast. And on the right, we have loaded the TWIA, which is the traveling wave signal extracted from the current measurement from the left relay and the right relay. So the straight one here is taken from the relay on the left of the line, and the green one is from the right. So we can see clearly the arrival of the first traveling wave from the fault, and then the reflection from the fault, and also the traveling wave from the other end of the line. And here is the same. So by using the difference between the two time where the first traveling wave peak arrives, we can easily calculate the fault location using the double-ended fault locating algorithm. And similarly, with the reflection from the fault, we can calculate using the single-ended fault locating algorithm. So this can be used if you don't have a communication channel between the two relays, or if you are equipped with only one relay. So from this calculation here, the fault location left pane is 8.065 kilometers, and the other one is 11.935 kilometers. So the error is very small, which means the relay locates the fault very accurately. So this brings us to the conclusion that using the real-time simulator, we can test the traveling wave-based relay using a hardware-in-the-loop test setup.